Hi, everyone. So first, I want to thank Dave and Alan for inviting us to give this talk. My name is Molham Aref. I'm here with my colleague, Kurt Stirewalt. We've been working together for a long time now, and we'll be jointly making the presentation today. I'll tee it up and give some background context, and then Kurt will talk about a specific case study. Kurt, do you want to introduce yourself to everyone?
Sure, thanks. And thanks, Dave, for having us. Hi, everyone. I'm Kurt Stirewalt. I'm the head of app development here at Relational AI. I've been working in this area for about, well, almost 11 years now, both at Relational AI and at a previous company where we had developed a lot of the techniques we're going to talk about today. And so, yeah, very, very excited to speak to you all. I'm very, very, very happy to have the opportunity.
All right. And I've been in the enterprise space since the early 90s, and I've had a chance to work with a lot of enterprises helping develop solutions that were primarily driven by machine learning and predictive analytics. Everything from credit card fraud detection to retail merchandising solutions to planning solutions, supply chain solutions, applications of wireless network optimization in the telecom industry, and so on. And so we have a lot of context from those experiences that we want to share with you today. All right, let's get started. So if you've worked in the enterprise, you know that companies and enterprises can be thought of as really big systems with overwhelming complexity, variability, and detail. In order to manage the complexity of the business, we have to build simplifying models. These models come in many different forms. You see lots of business people and people who work for large enterprises build financial models, typically in spreadsheets, or data models that they put in databases, or mathematical models of supply chain networks, or statistical models of consumer demand, for example, or statistical models that describe price elasticity, or even models that describe processes by which certain goals can be achieved, and so on. Now, typically, these models are limited or small or coarse or low fidelity in some way. And what we see a lot of in the enterprise is that these models are most commonly built with spreadsheets. In fact, most of our customers have thousands, if not tens of thousands, of these little spreadsheets everywhere throughout the corporations, with the corporation with lots of different flavors of data, stale data, with lots of bugs that no one knows exist. And of course, the other kind of commonly found model or system in the enterprise are enterprise systems like the kind you get from SAP or Oracle, where you have a lot of detail because you're tracking every item that you sell in every store with every customer and every employee, but you really can't see the big picture anymore. You lose the forest for the trees in these kinds of applications, right? And this is why the real work typically gets done in spreadsheets, because you can sort of get the abstraction that you want. And of course, we all know that the most useful models are the ones that can be built and maintained by the domain experts or the business people themselves, who can improve them over time, because the world is changing all the time, and nothing is static. If you take aspects of the model and put it in code like Java code or C# code or VB code, you've made that model inaccessible to 99% of business people, and basically you start getting model rot and things not working well anymore. All right, so this is just a very quick example of a model. This is based on something I found online. It's a model used by DuPont to compute a return on investment. And you can see here, a return on investment is, in this model, is computed by multiplying turnover by earnings as a percentage of sales. And then earnings as a percentage of sales is computed by earnings divided by sales. And earnings is computed by sales minus the cost of sales. And the cost of sales is made up of all these line items, okay? So, this is conceptually not that hard to understand. Different companies might do this differently. And in this case, this is DuPont's process. And so if we focus on this earnings equals sales minus cost, this can, we can relate to this, because if we're involved in a business or own a business or running a business, typically we're doing it to make more money. And typically we're trying to maximize our earnings over time anyways. And we can do that by either increasing our sales or reducing our costs or some combination of both. And typically the models that we build to help us get a handle on this have to, expose the levers that we can pull to increase earnings. And of course, when you get into sales, there are components of that. So sales is sort of total units sold. If you're projecting into the future, that's usually a forecast that you get from a statistical model, times unit selling price, which can vary over time as well. But you have to consider lost sales, like situations where you have demand for something, but you don't have the inventory for it. And how you transform that lost sales into future demand or lost demand or lost opportunities, as well as the potential for those lost sales to translate into loss of goodwill from your customers due to these shortages, which means that you might lose customers that come to you to buy something and don't find it. On the cost side, you have procurement costs, transportation costs, DC and store inventory holding costs, warehouse handling costs, capital costs, penalty costs. You have all sorts of factors that can go into cost. And of course, we live in a world that has limits and constraints like time and space. You don't have infinite money. You have to abide by the laws and the regulations in the place where you're doing business. And so those have to be factored into the model in terms of constraints that cannot be violated as you make business decisions. Like you can't work more than 40 hours a week and not pay overtime, for example. Okay, at least in sort of an hourly wage context. Okay, now once you build these models, unfortunately, you have to kind of map these models that are often very simple conceptually, very straightforward, very intuitive. You have to map them onto a hairball of technology. This slide here is a slide I received from the CIO of a customer of mine over 10 years ago. And he told me that this represents 2% of their overall IT footprint. And that, PowerPoint struggled to render this slide when it had 100% of all the systems that they were tying together. And each one of these boxes actually represents a set of technologies that was used to build the application that each one of these boxes represents. And you can see in an application-centric architecture like this one, you have applications like ERP, and it's basically its own silo. You have CRM applications, you have supply chain applications, you have human capital management applications, you have e-commerce applications. I've read a statistic recently that said that typical enterprise has something like 476 custom applications that they develop. Each is a silo, each built with its own technology, each is backed by its own database with its own database schema, even though it's basically an application that's being used in an enterprise that has a relatively small number of concepts that you have to understand in order to work in that enterprise. Okay, so you have the set of applications that are silos, and then you have a hairball tech stack that has databases like Oracle or Postgres or SQL Server or Neo4j or Cassandra or Mongo. And because every database has its own schema, and because business users typically want to look across data from all these applications, typically these databases are dumped into data lakes, and in some cases organized further into data warehouses, and that data can be accessed via a variety of BI and spreadsheeting tools, and then also accessed via a variety of machine learning and statistical modeling tools and technologies. Okay? And in each application, not only do you have a database with its own schema and so on, you have to typically program it in at least a handful of programming languages, and often 9 or more. So for the front end of the application, you might use a programming language or like HTML with CSS, JavaScript or TypeScript or PHP. If you have a mobile-based user interface, you'll use Swift or Java or Kotlin. If you are integrating with between the front end and the back end or other components of the application, you will do it via APIs and interfaces where you might use REST or graphical protocols, languages. The business logic for the application is typically programmed in Java or C# or Python or Ruby. The database that the application uses is accessed via database query languages like SQL or Sparkle or Cypher or Hive. The database will often have a stored procedure language like PL/SQL or T-SQL or Java. If you are using a predictive model to predict demand or churn or risk, you'll build that using programming languages like Python or R or Julia or SAS. And if you have an optimization, or if you want to do prescriptive analytics, you will use languages like GAMS or AMPL or OPL or MOSO. And if you want to provide end user analytics, you do that in spreadsheets and BI tools, and you'll have to program in Excel or Looker ML or Tableau and so on. And it really doesn't end there, because beyond the languages, you have to pick frameworks like React, Angular, Vue, for example, for front-end development, or other frameworks, web frameworks like Node.js or Ruby on Rails. You also have to pick integration frameworks like Kafka and Spark, and streaming and integration frameworks, I should say, or RabbitMQ and MuleSoft and so on. So it's really very, very complex. You might take a model that conceptually is very simple. By the time you're done mapping it on this technology, this kind of tech stack, you've now fragmented across hundreds of thousands of lines, actually more often millions of lines of code written in a variety of programming languages using a variety of frameworks. And of course, end users get further and further removed from the models, because end users are, you find more of them than you do, for example, application developers. And end users like to work in languages and systems that are declarative, like Excel and SQL. I underlined here on this slide any language that was declarative. I underlined it, as you can see. And so end users and power users and data scientists and so on are more comfortable at the level of SQL queries and Excel formulas. And by taking their model of the world and mapping it onto C# and Java, you made it very difficult for them to maintain and evolve those models. Okay, so how do you emerge from the software wasteland, to quote the title of Dave's book? Well, we think many of the problems with enterprise software are due to the inability to directly and exploit declarative knowledge, to keep things declarative in the way that end users want and understand, and in a way that end users can evolve. One symptom of this is you end up with large inflated project teams with non-technical product owners who know the domain, paired with non-business people who are fluent coders, but who have a little domain knowledge, and frankly, often don't care about the business that they're working in, and the ensuing tension that comes out of those kinds of interactions. Another symptom, of course, is that the implementations themselves are just incredibly complex and large, and very hard to understand. They require more and more technical people to support and maintain, and just become too expensive. And before you know it, people want to throw them out, throw the implementation out, or redo it, because it just becomes untenable to maintain what you have. So we've been working in this space, as we mentioned at the beginning, since 2007. We built a lot of enterprise solutions using what Dave describes as data-centric principles. We've done it sort of the old way, and we've done it the new way. And it's really out of a strong instinct for self-preservation that we had to find a new way of doing it, because doing it the old way is soul-crushing, and it's not something that we could do in a sustained way. All right, so we like knowledge graphs. We've used knowledge graphs effectively to solve the kinds of problems I just described. And by using them, we've ended up with models that are much smaller and easier to maintain and easier to reason over. And by using the right kind of technology, we end up with models that perform better and scale better than the mess that I just described. And so a lot of what we read about in both Dave's books, Software Wasteland and the Data-Centric Revolution, resonated with us. The only thing that I personally would change about those books is that whenever Dave refers to relational databases, he's typically talking about SQL databases, and perfectly understandable because the SQL database community has managed to co-opt this mathematical concept of relations and this idea of relations as a form of abstraction, which are fundamental to knowledge graphs, because knowledge graphs are all about modeling relationships directly. And so we like to make the distinction between SQL databases and the relational database paradigm, which are not the same thing. The other change we would make to Dave's books is instead of mapping or doing things the new way on top of what he calls graph databases, we think that graph databases typically don't have an ability to represent knowledge, to reason, to do sophisticated knowledge graphy type things. And so we would substitute a knowledge graph database or knowledge graph management system for graph databases in Dave's books. Other than that, we're in violent agreement with everything that he writes and his point of view on this. And thank you, Dave, for writing those books. And so with that, I'm going to turn this over to Kurt. Kurt, I'm going to stop sharing, and perhaps you can start sharing on your end.
Sounds good. Bring this up and go into presentation mode. All right, I assume everyone can see that. So thank you, Molham, for the background. I'm going to talk for a few minutes about some case studies and experience we have in actually applying these techniques, so that you get a sense of how we do what we do and where we've applied it. And I want to introduce you first to a case study that demonstrates the kinds of problems we've been using knowledge graphs to solve in a domain that we call decision management in large mutual funds. So to understand this domain a bit, suppose you're a mutual fund and you're trying to do what mutual funds do, which is to sell many different positions, buy and sell lots of positions so that you can eke out little bits of profit from each one. Maybe you hold some positions for a very short time, others for a very long time. Maybe you hold opposing positions at once. There are all kinds of possibilities, ways you can make money doing this if you're good at it. But one problem that you'll immediately encounter is that you have to relate trades involving both long and short positions at any given time. And the reasons for that, there are many. They all stem from regulations around how different trading behaviors are treated. Some kinds of behaviors are not legal. Some have different tax consequences, etc. Now, this is an interesting problem that is not obviously as interesting as it is until you get into it, but it actually requires some pretty sophisticated reasoning. And specifically, it requires a special kind of reasoning, recursive reasoning that is non-monotonic, which is particularly complex to reason about and is therefore pretty expensive to compute. What's also interesting is that each step in this recursive reasoning, this sophisticated reasoning you have to do, tends to involve some pretty expensive operations. In this particular example, each step involves doing what we call multi-way joins, where you have to literally join data from a lot of different sources together to make a decision. You have to sort very large sets of data on each step in this reasoning, etc. So it's one of those problems that has a lot of inherent complexity and an awful lot of tricky corner cases that you have to deal with. Now, we're working on this problem with a client who has a legacy system that's implemented in the traditional kind of imperative paradigm, imperative language and technology stack. You could think, just to make it concrete, think of Java or C# and a big legacy SQL database technology. That system is really large and very difficult to maintain. And just to give you some numbers, the code base comprises hundreds of thousands of lines of code, close to 1 million, actually. And they are having scalability issues with some of their larger portfolios that they need to work with. In fact, for some really large clients, the current system really can't handle to scale the analysis at all, and actually runs out of memory with a failure. So even though they've got this massive system, It's still not, it's awful to support and maintain. It's big, and it doesn't even scale very well. So we were engaged to develop a knowledge graph solution for these folks. And we found that we could actually compute the same results with a much, much smaller code base, somewhere between 1 to 2 orders of magnitude smaller. And the way we expressed the program was not only smaller, but it was also traceable to the relevant securities trading and tax laws, which is obviously a good benefit. And it's a big component of what a fund has to consider when they're making decisions, these individual laws. It's really important that you get them right because they're tricky, there's a lot of them, et cetera. So furthermore, our solution scaled much better than their legacy solution and was able to handle the large funds that they had that blew up their system, right? And so we could actually handle them. We did in a small number of minutes. It was up to about an hour. I'll show you some graphs later, things that they just couldn't handle at all. So to give a little more detail, this is on our methodology. This is a slide that I used to help explain to this client what we did to get these amazing results. When we did it, we did it as part of a little proof of concept, and they said, "Wow, how did you guys do this? And how did you do it in such so quickly and so effectively?" Now, the approach that I'm going to show here should be very familiar to any audience who builds ontologies like folks on this call. But it was definitely not familiar to the business users who we were supporting when we embarked on this project. So we basically looked to build the solution by understanding and declaring the ontology of the domain, and then writing rules to declare how to derive the results from the inputs. In this case, it was an evolving portfolio of positions made up the inputs, purchases and sales of securities, okay? Now, we all know that real enterprise data exhibit rich constraints, and that if you can capture those constraints, you can reason with great power to reduce the size of the code you have to write and to increase your understandability of the system. And so here's an example using our declarative language for expressing constraints, right here, if you can see my mouse. The first constraint right here says basically that if a position, you know what a position is. A position is a group of securities that you purchase. If a position opens on some day, so opens on position equals day, if that's true, that implies that the position closes on some later day, right? So opens on position equals day implies closes on position greater than or equal to day, okay? You'll see that we declare these kind of if-then constraints as logical implications using the keyword implies, right? And here's another one here, right? The second constraint says that if I have 2 lots, lot 1 and lot 2, and lot 1 relates with lot 2 until some day, then the position associated with lot 1 closes on that day, or, keyword or there, the position associated with lot 2 closes on that day. So this is an interesting aspect of the problem because it shows how these relations are treated for purposes of taxing the purchase and sale of securities that are involved in a relation, which is important when you're making these decisions. Now, we discovered a lot of constraints actually quite quickly once we started talking with business users in this domain, and it didn't take very long to start just kind of ticking off these constraints in the exactly like you see them here. Sometimes, if you discover enough constraints of a problem, you can actually use a reasoning engine to directly solve for the outputs given a set of inputs without even having to write rules. The analogy here is with, if you can remember, solving systems of equations back in high school math, right? You don't have to write a calculator. You can just basically, if I think of each equation as a constraint and I have enough of them, sometimes I can actually figure out what the values for X and Y are. That actually didn't happen in this case study, but we have worked in domains where this is possible. In fact, I'll allude to one later where we're doing replenishment optimization for clients, where we can actually model their replenishment networks as a set of constraints and literally just use reasoning technology to solve for that, rather than having to write a program to go figure out how to properly replenish stores in the face of change in demand. But we'll get to that in a minute. The other thing we do in our methodology is we declare knowledge in the form of rules that capture how, in this case, how funds make decisions around how to relate lots and the tax implications of doing so. Now, here are a couple of examples of rules that you see here. This first one says that a lot of shares is available on some day if the position associated with that lot opens on that day. Okay, you can probably read this pretty clearly. They verbalize pretty naturally. The second rule says that a lot is available on some day if that lot is available at the end of the prior day and the position associated with that lot closes on that or some later day. Okay, you may have to stare at this one a little bit, but it says, you know, lot is available on day if lot is available on day -1 and the position of that lot closes on some day greater than or equal to day. Okay? All right. So rules in this form are nice and clearly and compactly stated, and they're actually relatively easy to verify with a business client. Right? You can say things at this level, and clients will say, "Yeah, that stands to reason. It makes sense. That's how I think about the problem." And also, while they may appear very simple because they're so small, the calculations that we declare by them can actually be quite complex. So for instance, the rules shown here are actually part of a recursive cycle of rules. And the reason for that is this relation here, available on, is actually defined in terms of available at end of, as you see here. And we'll later see a rule for available at end of that refers to available on, right? So there's a cycle there. With a knowledge graph management system, you can actually reason with these rules and maintain the calculations they perform at scale, even though they have these circularities in them. All right, so here's, this is a pictorial view of a piece of the ontology, just to kind of give you a better sense of how it looks in this case study. And you'll notice from this diagram the prevalence of constraints, which we show here in these little purple symbols. Here's one, here's one, here's one, here's one, another, etc. You can also see a textual form of some of them here on the left. The notation we use for these ontologies is called object role modeling, which is one we used, and we use a tool called Norma to capture and record them. ORM, object role modeling, or ORM, is very good at expressing ontologies. You can kind of think of it as a distant cousin to OWL. And notice here that we've identified several concepts such as position, day, long and short, etc., as well as relationships like position opens on day, position closes on day, etc. I guess in total, the ontology for this problem comprised about 35 different concepts. Okay, and I'll give some more details about the rules and constraints here in just a moment. Now, what's interesting is if we take a look just to kind of see what we're expressing in terms of constraints, these are quite expressive. This one says that the opens on day of a position must be less than or equal to the closes on day, right? And so I do that with this less than or equal constraint that I can connect to the day roles of these two relationships here. Okay, and it gives you some sense of the flavor. These are things that you learn when you're modeling the ontology with your business clients. You put them in, and they make your models much tighter and more expressive. And of course, you can then use them later. Other constraints express things like subset relationships. See here, here's another less than or equal. This is called a ring constraint. It's useful when you have relationships that can potentially have that map the same kind of concepts to one another, and so could potentially form a cycle. We identified over 50 of these constraints in our case study, just to give you kind of a sense of the size of it. Okay. All right. As I mentioned, we also came up with some rules to infer new facts. Here are some examples of rules, just to illustrate more of the constructs that are available and to more clearly indicate the recursion that I mentioned earlier between available on and available at end of. You can see here this rule for available on right here refers to available at end of, which is another relation. That relation is defined by a rule here, and it refers to the available on relation. So clearly it's recursive in nature. Now, to reiterate the point from earlier, notice that each of these rules is very compact and can be verbalized meaningful in English. This is really in stark contrast to what you typically see in an imperative implementation. All right, now this is an interesting graphic on this slide. We actually took the whole set of rules and constraints that were required to implement the problem for our client, and we printed each page in thumbnails, and all of them are shown here. And literally, this is all of the code. Okay, and you'll see that it fits on one slide, and you can see that, you know, we didn't cheat. You know, these were printed pages, so you know, there's what, maybe 50 lines, 55 lines per page. But you can see these are literally printed pages, and there are only, what, 7 of them, right? And it all fits on one slide. What you're seeing here in these thumbnails corresponds to about 100,000 lines, we estimated, of imperative code in the legacy solution, right? So clearly this is an improvement, right? It's an improvement just in terms of being able to understand the domain and to maintain. You clearly won't need as many people to maintain a program like this as you would for 100,000 lines. And as I mentioned earlier, I can't really show you more examples than the ones I already have, but these things are traceable back to you know, securities and tax law. Okay. Now, so what do we do with all these rules once we've declared them? Well, our knowledge graph management system takes the set of rules and constraints and executes them, as Molham alluded to earlier in the talk. We do this by building a structure called an execution graph, which I'm showing here. And an execution graph, unfortunately, there's a bit of conflation of terms. An execution graph is different from a knowledge graph. I'll go into more details here in a moment. But in this case, what we're showing, this execution graph, it's a computation structure that a knowledge graph management system uses to elaborate and incrementally maintain a knowledge graph. Okay, so if you can think of this graph here as being like a program, that program is running to basically build out your knowledge graph and maintain it. It's automatically constructed from a rule set. So once I declare the rules that I showed earlier, you get this for free. Any recursive dependencies among the rules manifest as cycles in this execution graph. And in fact, what I'm showing here to the left is a strongly connected component of the execution graph that we used in our mutual fund analysis problem. And this particular one comprises about 31 rules. Okay, so this is not the whole thing. It's just a recursive kind of kernel or subgraph of the whole solution. Now, some of the edges, which show here as dependencies, depict non-monotonic reasoning, and in fact, the ones in red show cases where the reasoning required to maintain the knowledge graph is actually non-monotonic. What that means is at some stage of the application of these recursive rules, some information is derived that may later need to be retracted as more information becomes known. Okay, so there's some things I can know, and then later as more information is learned, I can find, that wasn't actually true, I need to change it. This often happens when recursive rules involve negation or sorting or other forms of aggregation. Okay, so this is a generally known problem. And moreover, when you build these execution graphs, in addition to being able to support this kind of non-monotonic reasoning, recursive reasoning, we can support incremental maintenance, which I'll go through an example of later to kind of make the point clear. With incremental maintenance, we can use the structure of the graph, of this graph here, to basically patch up parts of an elaborated knowledge graph that will need to change in response to small changes in the inputs that derive them in the first place without having to recompute the whole graph from scratch. That's obviously a very powerful capability because it's going to improve the efficiency of your reasoning and the kinds of applications and solutions you can build using it. And again, you get this very powerful capability for free using the approach we're describing above. Execution graphs can also be used to carry along the provenance of reasoning, which is sometimes useful in applications that need to track provenance and ask what if and why questions. We actually did this, it's not yet supported in our knowledge graph management system where it's on our roadmap, but we did implement this in a previous lifetime in another company. And so again, that's on our roadmap for the new platform as well. All right. Here's a quick, you don't need to read all the numbers here, but just to make it make sense, this is actually a tweak of a report that we did at the end of our project that shows the performance and scalability of our approach on a number of data sets. What's interesting about this is this bottom right corner where you see the infinity sign. This is a case where the legacy solution, the performance of the legacy solution actually had never terminated, right? It blew up with the out of memory error that I mentioned earlier. This is one of those data sets that it was just too large for it to process. By contrast, we did it in 5,500 seconds at the time that we did this analysis. We've actually since been able to improve the performance of that even more. But the point is, this is not infinity, right? So even though this is something that blew up the 100,000 line algorithm, we could do it quite efficiently using a knowledge graph. Okay. All right, that's the case study. I'll say a little bit about some other experience we have in enterprise context. And I won't go over this in just the interest of time in much detail, but we've done work, as Molham mentioned earlier, in planning, inventory optimization, price execution, and forecasting. All of these we found good applications of knowledge graphs and knowledge graph management systems to do the reasoning. And we got the same kind of benefits that I've kind of mentioned before in the previous case study, right? So what we've observed, yeah.
Yeah, I just want to chime in. I mean, that work was done for some very large enterprises that you all would recognize. 3 out of the top 6 largest retailers in the US were running their either merchandising operations or their supply chain with solutions that were built with knowledge graphs and with the methodology that we're describing to you here. So this is, of course, they weren't buying knowledge graphs per se. They were just buying an application that worked, and they were buying it at a price that they liked, and they were buying it sort of with a risk profile that they liked. We had sort of at the time in our previous company, we were just selling the applications that we were able to develop at a fraction of the cost of our competitors. At Relational AI, we decided that moving forward, we think that actually the plumbing to help people do this in general is very valuable as well, and that's what we're going to be taking to market. So, anyways, I didn't want to interrupt, but I wanted to highlight.
No, thanks for mentioning that. I appreciate it. Yeah, this is definitely not a toy, right? And these are definitely not toy applications. Just as he mentioned, if you look at the size of the clients that we've worked with.
Yeah, and the size of the data sets, and the complexity of the business logic. Okay? So one of the applications, for example, had 50 terabytes of data being managed, right? So, try to put 50 terabytes in a toy graph system, and it just doesn't work. And unfortunately, our community has a lot of technology or technologies that make for great demos, but don't work for complex problems with large data sets. And that sometimes gets in the way of having credibility in an enterprise context. And what we were able to show here is that we can basically make this work at the largest enterprises.
Yep, absolutely. And moreover, we've been doing this since 2013. So this isn't new. It's funny too. In every one of the examples that Molham just mentioned, we went in to replace a legacy system that was built using the traditional approach. And we see a 1 to 2 order of magnitude reduction in code size, in addition to just being able to handle it at all. I should also mention that most of our experience comes from clients that actually do have a legacy system in place. In fact, all of those big companies that Molham just mentioned a moment ago, they had a big system in place and they were having problems either with its performance at scale, their ability to maintain it due to all the accrued complexity, that Dave so nicely described in the Software Wasteland book, or both, right? And honestly, they just wanted something. As Molham mentioned, we didn't sell them on knowledge graphs. They just wanted something better, and they didn't mind rewriting it from scratch, right? So that gives you some sense of what we've seen. Some of the large solutions that we've dealt with, some of these biggest clients, they have on the order of 1,000 rules, maybe 1,200 constraints, just to give you a sense of how big this can get. But again, in terms of printed code, that comes down to less than 20,000 lines of code printed. And you compare that with hundreds of thousands or millions of lines of code in the other approach, you can see the benefits. We also would commonly see development cycles of around 3 months okay, from concept to production. And I'm especially proud of one, in fact, one of the clients that Molham mentioned earlier. I'm especially proud of one that we did with a very junior team of new developers that allowed that client who has many stores. They were getting ready to open a new category of stores. And they basically opened those stores, assuming that our solution would be in place at the time when we said, which was only a few months away from when we started the project. And we hit it, right? And it was very successful. Dev teams are never, just some other statistics, dev teams are really never larger than around 5 persons. These systems have other benefits as well, such as allowing users a global view of really large data sets, using streaming data to do near real-time forecasting. Using some of the capabilities I'll explain here in just a moment. And again, as Molham said, much of this work was done in big retail applications, clients such as Walgreens, Kiabi in France, Whole Foods, et cetera. Just a whole slew. Okay. All right. So let me now pivot to how we do this. I've kind of explained the what. But I haven't really given you much insight yet into how this works and how it scales so well. So let me start with this idea of an execution graph. And again, I apologize, there is a little bit of term conflation necessary, and I want to just go ahead and clear it up in one place. So we've been talking about knowledge graphs, and knowledge graphs comprise nodes and relationships. Both of these concepts in a knowledge graph context, nodes and relationships manifest as relations in our knowledge graph management system. In particular, a node, a knowledge graph node is a unary relation, or class of nodes is a unary relation in our knowledge graph management system, and a relationship is a multiarity relation in what's called graph normal form, also called 6NF or 6 normal form. Now, what's interesting is that both nodes and relationships are first class citizens in our knowledge graph management system. And in our context, these relations are either asserted or derived, and may or may not be stored. Okay, and there are often performance trade-offs you can make by deciding when to store and when not. These kind of trade-offs are made automatically by our knowledge graph management system. A derived relation, which is also called a view, is computed and incrementally maintained with rules. Okay, you can think of those as, I showed you some rules earlier. You can think of them as queries as well, right? If you're more familiar with that terminology. And what's nice about this is that you get very expressive reasoning over this knowledge by virtue of these execution graphs, which are constructed automatically from the rules and constraints. Now, again, it's unfortunate that there's a conflation in terminology. And just to remind you, an execution graph is a structure that computes and maintains a knowledge graph. It's distinct from the graph that it computes and maintains. Right? It's unfortunate they're both called graphs, but I don't know what else to do. Hopefully the context will be clear in the examples that follow. And another thing about execution graphs that's great, as I'll show, is that they enable very efficient allocation of resources to maximize parallelism and concurrency, as well as incremental maintenance. And in fact, our big claim is that by virtue of directly encoding declared knowledge, as I showed above, what we found is that good knowledge representations lead to more performance solutions. Right? That's a bit counterintuitive. If you talk to folks who swear by imperative technologies and legacy systems and application-centric design, but we found it to be true. All right, so to make these points clear, let's look at an example of an execution graph to just kind of to understand how it works. Oops. Yeah. All right. So I usually motivate execution graphs using a really simple program written in the imperative paradigm. And this is really stupid simple, but it does fit on one slide, so it's nice just for that. This simple program on the right has 3 statements that compute over 3 inputs, right? Let's see, I'm sorry, J, K, and M. Those are the inputs, okay? And they compute 3 outputs, I, L, and N, okay? You don't have to, it's a silly calculation, but hopefully it'll serve the purpose. Now, in a traditional implementation, we would deploy this program, okay, by doing some kind of staging or gathering of all the input data, And then we would run these three statements in order, and then we collect the outputs and do something with them. Okay, that's the kind of the traditional way you think about deploying these kind of imperative solutions. Now, by contrast, in a knowledge graph, if you want to implement the same program, we'd replace each of the statements by rules. I don't know if you saw it from the previous slide, but the assignment statement and the semicolons went away. Instead, I'm replacing with rules, right? Def and no sequencing or ordering there. There's no inherent ordering over the rules. They're implemented, they're independent modular data dependencies between the computed values that have to be calculated before one's used, but you don't see any explicit sequencing operations, okay? And that makes more of the parallelism that's inherent in the problem easier to discover. It's also more natural to come up with these rules in any order when you're doing knowledge acquisition with a client, right? You often will find them piecemeal and have to kind of stitch them together at the end. Now, what I'll show next is how to take these rules and automatically construct an execution graph that evaluates and maintains them. So let's just start going through it. You'll see the rule in red. I'm showing how I'm constructing the graph for that here. It manifests as an execution subgraph with an execution graph node representing multiplication here in blue. Generally, in these diagrams, the data that are shown in green are relations, you know, and you'll notice how data from those relations flow into and out of the blue nodes. Okay, and again, the blue nodes are constructed from rules. Now we add the second rule. Okay, and you can see I'm doing a little sharing there. The relation J now kind of feeds into both this execution graph node and also this one. And I'll add also add the third rule. And notice how we've shown how data like J fan out, you know, to feed multiple nodes of the execution graph. And now we've got it. Okay, we've basically got the execution subgraph for these three rules. Now, it's a simple example. There's no recursion, okay, but hopefully it'll suffice to give you a feel for how these execution graphs just get constructed by rules. Okay, nothing really super novel or new yet. Okay, so now how does this help with speed and parallelism? So one of the things you'll notice about the structure of these graphs is that it helps us to find opportunities to optimize calculations through parallelism. Any two calculations that are not data dependent, okay, there's not a cycle or a path that connects one to the other, may execute concurrently. And in fact, if you're given an execution graph, the breadth of the graph will tell you immediately the maximum number of tasks that can be performed independently. In this case, it's 2, okay? And also the depth of the graph indicates the shortest number of calculation steps required to compute the graph from scratch. That happens to also be 2 in this case because of this chain here, okay? So to fully evaluate this calculation from scratch, notice we can provision 2 cores to run in parallel, computing independent subgraphs of this execution graph, and note that the longest sequence of calculation steps is 2, okay? So, you know, whereas, you know, if we had done these things in sequence, you know, statement 1, statement 2, statement 3, it would have taken 3 steps on 1 core. We can trivially parallelize it by putting it in the form of an execution graph. Okay, so this allows us to throw hardware at calculations to speed them up. And, you know, I don't show it here, but there are other forms of parallelism that we can discover and exploit by virtue of a clean declarative modeling language like the one I've shown. For instance, when relations are large, okay, we can often use multiple cores to compute the same rule for independent slices of the source and target relations. We call this domain parallelism, in contrast with the task parallelism that I just showed. Our knowledge graph management system supports both domain and task parallelism to maximally utilize cloud resources that we allocate to these solutions. And this by itself is nice because there's nothing worse than paying for a big honking machine by the hour and not eking out every little bit of value from that investment. And it's actually a funny story from a previous life. We, you know, as I mentioned, we've been doing this before. We have similar technologies before. We actually had a case where rack space servers were actually overheating, and the rack space provider had to put in new air conditioning units because we were so fully utilizing all the cores on the machines we were getting. interesting. So we have anecdotal evidence, at least, that we are indeed using these resources maximally. Okay, so bottom line though is when you use a KGMS, you benefit from massive parallelism without having to really think about how to parallelize your code. And in addition, you get this benefit. You get additional performance by virtue of incremental maintenance, which I'll now demonstrate. Okay, so whoops, got a delay here. So suppose we fully evaluated a calculation such as the one I showed above, and now we now have to update that calculation to reflect small changes to the inputs. Right? So for instance, suppose I've run the program here on the right to compute I, L, and N, but now the user modifies the value of M. Now, if we've built the solution using the old way, the imperative paradigm, you have two choices. You can either rerun the whole program from scratch, or you can implement a variant of the program that operates over a calculated data set with a specific set of changes to kind of surgically modify just those outputs that need to change without recomputing it from scratch, right? We've probably all done this at some point in order to improve the throughput or processing of some job we've built. And neither of these is ideal. Recomputing from scratch is often just wildly inefficient. And surgically updating the calculated outputs based on changes to the inputs, it's the right idea, okay? It's the right thing to do. But if you have to program that up by implementing each of these variants, each variant might actually be trickier to code up than the original program, and it's a source of code bloat and also a big source of errors. Fortunately, a knowledge graph management system can automate the incremental maintenance of calculations in order to provide the same programming benefits of writing the program just once with the efficiency benefits of having a maintenance variant for each possible change to the inputs. So to make this clear, come on. I'm not sure what my machine's thinking, but it is not, there we go, okay. All right, so to make this clear, let's suppose we've evaluated the execution graph on real data and that the relations are populated as I've shown here, right? I've changed the names of the cells with their actual values at a point in time, just to make it clear. At this point, maybe I change relation M from 4 to 5, okay? And at this point, the graph is no longer consistent, right? Which is what we're showing in red here, right? Some of the derived relations are not populated as dictated by the rules that derive them. In this case, it's the third rule for deriving relation N, right? 12 is not 3 times 5, okay? So to bring the graph into consistency to reflect the invariance of these rules, we can basically allocate a core, okay, to just that little subgraph to update to update that part, and then we're done. All right, I didn't have to reevaluate the whole graph. I could just evaluate that little piece that was needed. So incremental maintenance, the virtue of it is it focuses computational resources to just that part of the execution graph that needs to be repaired. We can often update the that was a simple example. We can also update the outputs just by knowing the changes, i.e. the deltas, right? So for instance, if one rule calculates the sum of 100 or maybe even 1,000,000 integers, and one of those input integers changes from 202 to 200, there's no reason to compute the entire sum. Rather, we just deduct 2 from the previously computed sum. You can just imagine the ability to use algebraic identities and all kinds of neat little things you learn in high school to optimize these calculations in the face of different maintenance variants, especially when you have aggregations based on the deltas being applied. And again, all this is automated so that you don't actually have to think of that, even though it is an interesting topic, but you can just benefit from it merely by using a knowledge graph management system, as was shown. And that's all I have for now. I'm going to stop sharing and hand it back to Molham, but thank you for your attention.
All right, thanks everyone. Just wanted to just very quickly show you some references here for some of the technology. I know when we were prepared to give this talk, we were asked to share technical references. So share the screen here. And can you see that?
Yep.
Yep. All right. So our team is about 50 people. We're about 50 people. We've been around for a little over 2 years. We are working with a handful of clients that where we're doing some of the work that the kinds of work like Kurt described earlier. We do have a fairly technical team because it's not easy to build knowledge graph management systems that work beyond toy problems and work for complex knowledge and complex business problems running on large data sets. We publish a lot of our research in various conferences and workshops and journals and so on. So we've done work on worst case optimal joint algorithms and sort of advance the state of the art and state of the practice in the way that relational systems are built, so they don't have a lot of the limitations that SQL-based systems do have. We've done work on semantic query optimization, again rethinking relational query optimizers to work in the context of knowledge graphs. So keeping the best of what that technology had, but also adding things that are important to make relational paradigm work with knowledge graphs. We've done things on, done work on relational learning, and have advanced the state of the art in terms of how you do machine learning and statistical modeling in the presence of knowledge and knowledge graphs. And our system will be GA at the end of this year. If you're interested in working with us before our system becomes GA, please don't hesitate to reach out to myself or Kurt. So our email addresses are firstname.lastname@relational.ai, or reach out to Dave or Alan, and they'll be sure to connect you to us. So with that, I want to thank you for your time and your attention, and looking forward to being part of this community and attending the talks here, and hopefully working with some of you in the future. Thanks again.
Thanks, guys. Bye-bye.